Welcome back to Physics 101, where we would be discussing about Chapter 12, Fluid Mechanics. Our first question is physics that is applied to biology. We are asked to calculate the difference in blood pressure between her feet and the top of her head for a person who is 1.65 meters tall, and the additional outward force that the vessel needs to withstand in her feet compared to her head. Given that the vessel is 2 cm long and 1.5 mm in diameter. For part A, we know that the change in pressure is equals to density times gravity times height. With this, we can get the change of pressure at the head and at the feet. Knowing that our height is 1.65 meter, however, we are not given the density of the blood. So, we'll just assume that the blood has the same density of water, which is 1000 kilograms over meter cube, and our gravity would just be 9.8 meter per second square. Plugging in our values to our formula, we would arrive to the value of 16,170. For part B, we will use the definition of pressure, which has the formula change of force is equals to the change of density times the area of our vessel, which is a cylindrical segment that has an area of pi times the diameter times the length, which is also the height. Before we plug in all our values to our formula, we would first need to have the correct units in our variable. We must first convert the diameter and our height into meters because our density is in meters. We have to do this in order to have the correct final answer. Since we know that 1 meter is equals to 1000 millimeter and 1 meter is equals to 100 cm, we can easily convert our values into meters. Now, plugging in all our converted value, we would arrive to the final answer of 1.52 newtons. That would be the force the vessel would have to withstand. Now, for our second question, we have a barrel that contains 0.120 meter layer of oil floating on water that is 0.25 meter deep. We are asked to find the gauge pressure at the oil-water interface and the gauge pressure at the bottom of the barrel. For part A, we can solve this by using the formula gauge pressure of oil is equals to the density of oil times the gravity 9.8 meter per second square times the height, which is 0.12 meter. Plugging in our value, we would arrive at the answer of 706 Pascal. Now, for the total gauge pressure at the bottom of the barrel, we can solve this by equating the total gauge pressure to the sum of the pressure of the two liquids. We already have the pressure of the oil. Now let's solve for the pressure of the water. We are gonna do the same thing when finding the pressure of the water. We know that the density of water is 1000 kilogram meter cube with the height of 0.25 meter and the same gravity of 9.8 meters square. Times it all up, we would get 2450 Pascal. Now, for the final step, let's add the two pressure to get the total gauge pressure at the bottom of the barrel. We would arrive at a final answer of 3.16 times 10 cube Pascal. Now there you have it. Now for our last question. Our last question is an interesting one, and it's all about black smokers. Black smokers are hot volcanic vents that emits smoke deep in the ocean floor. Many of them with exotic creatures, and some biologists think that life on Earth may have begun around these vents. The vents range in depth from about 1,500 meters to 3,200 meters below the surface. We are asked, what is the gauge pressure at a 3,200 meter depth vent? To find the gauge pressure, we'll use the formula density times gravity, which is 9.8 meter per second square, times our height, which is 3,200 meters deep. Since our question states that the density of our water does not vary, we will use the density of the seawater so that we would be exposed to different water densities. And the density of seawater is equals to 1030 kilogram meter cube. Now we have all our values ready for our formula. Let's plug it all in and we would arrive at a final answer of 3.23 times 10 raised to the 7 Pascal. However, we are not yet quite done. We still have one final step because the question states that we would need to express our answer in both Pascal and in atmospheric pressure. Our final step would be a simple conversion of Pascal to ATM. We would just need to divide the answer we got to 1.0 times 10 to the 5th because we know that 1 ATM is equals to 1.01 times 10 to the 5th Pascal. After converting, our answer would be 320.13 atmospheric pressure. Now, what a fun physics session we had today. It's too bad that's all the time we have. Thank you so much for listening. Till next time. Now tune in for more physics solving fun.